very excited to have now our scientific panel of the day, Data Science and Climate Change. And our moderator for this event is Francesca Dominici, a professor of biostatistics, population, and data science at the Harvard School of Public Health. She also co-directs the Harvard Data Science Initiative. Her research focuses on data-driven policies for human society, and more specifically, Professor Dominici aims to develop and advance methods of analyzing heterogeneous data sets to better understand the health impacts of environmental threats such as air pollution, and to inform society. So, Professor Dominici, thank you for serving as the moderator for this year's scientific panel, and I welcome you here today. Thank you.
Thank you. Thank you. I am a big fan of the Women in Data Science Conference, and it's really my pleasure to moderate this really fantastic panel. So I will be introducing the panelists for today, and then each of them will provide some comments and a remark about the research, and then we will open up for questions. So it is really with great pleasure that let me introduce the three panelists. So one of the first panelists is Ronita Burden from University of Cambridge. She's an assistant professor of sustainability in built environment at the Department of Architecture and at University of Cambridge. Dr. Ronita Burden is an architectural engineer and urban studies educator with a PhD in urban engineering. She believes that data-driven intelligence of built environments can effectively address sustainability goals and policies. Her research is in the niche sector of sustainable built environment to inform health and energy decisions in a changing climate and low-income community. Burden uses data-driven methods that couples architectural engineering, AI, and machine learning with social sciences to provide a built environment solution for health in resource-constrained society. So welcome, Ronita. Our second speakers and panelist is Sasha Gluccioni. Sasha is a research scientist at Hugging Face, where she works on the ethical and societal impacts of machine learning models and data set. She's also the co-chair of the Carbon Footprint Working Group of the Big Science Workshop and a founding member of a Climate Change AI, an organization which catalyzes impactful work applying machine learning to the climate crisis. Her goal in research is to contribute towards understanding the data and techniques used for developing machine learning approaches, as well as to contribute to the growing field of AI for good. Apply AI to high-impact societal problems like climate change, health, education, and humanitarian responses. Welcome, Sasha. And our third panelist is Jessica Trensick from MIT. She's a professor in the Institute of Data Science, Data Systems and Society at the Massachusetts Institute of Technology. Her research examines the dynamic cost, performance, and environmental impacts of energy system to inform climate policy and accelerate beneficial and equitable technology innovation. Her project focuses on all energy services, including electricity, transportation, heating, and industrial processes. Her work spans solar energy, wind energy, energy storage, low carbon fuels, electric vehicles, and nuclear fission, among other technologies. So it's really a pleasure to have you all. And I'm going to turn to Ronita first, and then Sasha, and then Jessica.
Thank you so much, Dominici. And I think I've prepared a few slides to show exactly what I mean by data-driven design. I primarily work on deep built environment design. That means I'm trying to develop design solutions that can decouple energy and health burdens from poverty. So not necessarily you have to be bearing those burdens just because you are poor. So what do I mean by data-driven built environment design? So I am a person who will collect a lot of data in terms of sensors, in terms of modeling, in terms of real-life CFDs, and develop a general environmental aspects of the built environment. Apart from that, I also generate a huge amount of qualitative data sets from practices, from cultures, which represent, and then I combine these two in order to develop goals for sustainability in terms of both low carbon living and space and life efficiency. More or less, I use a lot of innovative data sets that can come from sensors, also can come from TikTok videos or films, and definitely use a lot of conventional methods of data collection, which are more human-centric. And thereby, my research group responds more towards these four broad sustainable development goals of gender, clean fuel, energy, and health, and primarily sustainability of the communities, typically low-income communities, through design. And my response to I use design as more of a solution, and I seek for outliers, and I try to develop design solutions from those outliers. I got interested because I was very much interested in the interconnections and the tensions of urbanization that our global south is currently facing, which is a shortage of shelter, and definitely they have feedback loops in terms of energy and health. And given that we will be seeing an exodus of these sort of affordable housing moving ahead, there's a need to understand how these housing would look like, feel like, and what and why about these sort of housing. So I studied extensively in the global south. Majority of my studies are located in Mumbai, where the new phenomena or new typology of housing was being developed. What it actually does is it actually replaces these potential informal settlements, and they develop in situ development. So for the first time, the housing access is kind of solved in the sense that they don't have to move out of the city in order to live in these sort of houses. But surprisingly, I was seeing most of these houses were cropping up throughout the city, and a city where almost 50% of the population lives in similar kind of settlements. It raises a question that how do these people live? Do they like it? It's a better form of living, and they get these apartments for free. So I started looking at from an outside to an inside. So I started using a lot of GIS and data science methods to cluster the city and try to find out, and from the top or the footprint, you will see this sort of environment, this sort of built environment is what we can see. So I wanted to see what was the heat stress like, and we found out that compared to all the other typologies of houses, we found that this sort of houses had a high heat stress index, and that kind of question that if these are newly built houses, how are they performing indoors when the outdoor heat stresses are so high? So we started looking at the relationship between design typology and health burdens, and so we only looked at these type of houses and the types of design that were actually there in catering to the needs of these type of houses. So we found out that there were like an X type, there was an I type, and an H type. The I, X, or H are primary representation of the corridors or the common areas, how they were built. So typically I means you have rooms around a very prolonged corridor, and similar to H and X. And we got interested because we started looking at tuberculosis data, and we suddenly found that basically the government of Maharashtra was finding that people who move into these houses were reporting a large number of tuberculosis. And I was at the same time I was looking at energy access and energy behavior in these sort of houses. So I combined those two data set together to see if there was a correlation between these two sort of the designs that were being used versus what was the tuberculosis shift. And interestingly, we found out in the X type, people who had reported tuberculosis were basically previous cases when they were in the slums and they shifted to these houses, whereas the I and the H type, which reported high incidences of tuberculosis, were from people people who had actually lived in these houses for more than 5 to 6 years. And that was kind of appalling if when there is a global national target of India to kind of eradicate tuberculosis by 2050, whereas there is another national target of providing these sort of houses and building around 2 million of these houses by 2022, which is this year. So we were more interested that if this is what the health burden is, let's look at the pollution burden. And we did a lot of measurement campaigns. We actually started, rented one of these apartments, emulated their lives. And so you can see me cooking along with my very brilliant researchers who helped me. And we were emulating their lives whenever they were cooking. We were also cooking, and tried a different sort of scenarios. Also did a huge amount of focus group discussion, because one of my data set is actually intangible social data sets, which does not get covered in terms of census. And that led us to understand what was happening between the slums versus this. And when we compared that, we found out, whereas in the slums, the pollution was more of an effect from the outdoor pollution because of infiltration. In the slum rehabilitation housing, it was actually being trapped because of poor design. And that led us to see if technology and behavior are correlated, and if technological solutions can act. And we found out that by providing a ventilator, it can actually reduce by 98%. But when we looked at the condition of ventilator, we found out that typically it's not provided, an extract fan is not provided, and it's costly. And if somebody actually installs it, it's actually, in order to make it operable, they have to kind of close the whole window. So there's definitely a problem in the window design. So when we do normal technology level simulations, the window would perform perfectly. But when we integrate the behavioral data, it doesn't work. And that I got more interested, and I started looking at the thermal comfort. And we realized in engineering models, we use very standardized models of clothing and comfort variables, whereas here we found out it was more of gendered, because of the agency of and the cultural practices around these places do not allow for adjustment of clothing, rather than for one particular cohort of gender, whereas other cohort, they could actually have quite a agency in terms of controlling their thermal comfort. And that led us to show that one particular corridor can actually make or provide agency to people, where we found out that in HNI type, they were primarily, because it was more of an access corridor, it was primarily being shut off by the women and not being used by the women. Whereas in the X type, you can actually see a small little entrepreneurial activity that is being done here when they will sell these garlands, flower garlands in the evening. So it kind of provided more agency, and we started looking at what happened during the pre-COVID versus post-COVID. And we found this data on their electricity use, and we found that 2020 during lockdown, they were actually consuming much more than probably they could also afford. So that led us to see what is the energy landscape there. And it was impossible for us to actually go and do the huge research during the COVID time. So we adopted a method called energy found films. So we picked up all the films that were showcased or were using this as their base, or the protagonists belonged to this sort of place, and had sufficient amount of images which reflected the lives of these people. And we were this is the picture what you see in the real life from a Google Earth image, versus this is what the film film scene was showing. So it was exactly replication of what was happening in real life. And we were trying to see from the films whether we could actually extract energy transition. And we found out, yes, televisions and toasters appear quite late in the films, whereas simple things like fans and switchboards were quite earlier in the film. So we could make an estimate, and it can work as a secondary data set or an innovative data set for understanding energy transition. We are currently working in India and South Africa to understand research from the perspective of the researched. So we gave agency, we taught women how to film their lives and made 15-second videos, and then we extracted data from there to understand how they lead their life. And yeah, that brings to the acknowledgements of all the fantastic people and funders who have supported my work. Thank you so much.
Thank you, Ronita. Fascinating. I'm going to turn it to Sasha.
Okay, good. So yeah, I'm Sasha. I'm currently a research scientist at Hugging Face, working on AI for societal benefit projects. Before, I used to be a postdoc at Mila AI Institute. And before that, I used to do applied research in data science and machine learning in finance and customer service. I have a lot of research areas and projects that I'm working on and interested in. Broadly speaking, in the AI for social good sphere, today I'll focus, of course, on the climate side of things, but I'm also interested in ethics and fairness applications as well. So I'll talk to you about a couple of different projects I'm working on just to give you an idea, essentially, of the different opportunities and data sources there are, and hopefully inspire you to get involved in your own way. Just to take a step back, a couple of years ago, in 2019, we wrote a paper called Tackling Climate Change with Machine Learning. There's over 20 authors. It actually just got published officially. It was a preprint until like a couple of days ago. Now it's officially on ACM. So it's something like 50 or 70 pages now, with all these different ways in which machine learning, AI, more globally, data science can help tackle climate change. After this paper was written, a bunch of the co-authors came together and created Climate Change AI, which is, as was said, this volunteer organization to help people get involved, to give them resources, to give them support in essentially creating, deploying AI and climate change projects. I know this slide is always kind of a lot, but the idea is, you don't need to read everything, but the idea here was that there's so many different techniques in AI and data science, and there's not a single solution to climate change. So it's actually a lot of different opportunities. So what we did is we created this kind of heat map on the y-axis. On the left, you can see the different sections of the paper. Everything from electricity systems to transportation, industry, climate protection, et cetera, et cetera. And then we have different approaches, right? Computer vision, NLP, reinforcement learning. And so the idea here is to say, okay, well, you're good at reinforcement learning and you're interested in, transportation. There are these projects that you can work on. These are the things that, these are the people who are working on these projects. This is the progress that's being made. So it's also to help people kind of see who's who, what's what. So if you're interested in learning more about any of these topics, we have our website, climatechange.ai, where we have interactive summaries, where we have a wiki that we created with kind of more targeted information. Personally, I wrote the education and finance sections of this paper. So if you're particularly interested in, for example, education or the impact of climate change on finance, you can feel free to reach out. To give you a kind of a feel for the kinds of projects I've been working on in the last couple of years, back in my previous life, I used to work at Morgan Stanley, which is a big finance firm. I quit because I felt that I wasn't doing enough to tackle climate change, essentially. But at the time, a lot of my work was analyzing financial disclosures, which are these like huge documents of like hundreds of pages where companies like say, well, we've made this much money and we have, factories in these places and blah, blah, blah. And they're actually technically obliged to disclose their climate risk, which is interesting because this is not something that a lot of people know. They're, for example, in the US, companies are obliged to say, these are our vulnerabilities with regards to climate change. This, for example, we have waterfront properties that are liable to flood. We have supply chains that are dependent on this, this, and this. But it's really, really hard to find this information because it's like there's 200 pages and it's a couple of paragraphs. So we actually trained a model. We've worked with financial analysts, sustainability analysts to label some data. We trained this climate QA model, which lets you drag and drop a PDF. And then we'll find the relevant passages, and we'll even say like what kind of disclosure it is, like whether it's insurance related or extreme weather related and things like that. So this is one thing. So there's a lot of textual data out there about climate change, and there's a lot that machine learning can do to analyze that data. It's really important to work with people who will either use your tool or who are doing related work, because they're the ones who are going to tell you, because we had our ideas, we had like all these things that we could do with machine learning, but they really said, well, this is what's relevant, this is what's useful for us, this is what can be used. So that's a really important part of the equation. Another project I was working on last year that's actually deployed now is butterfly identification. So butterflies are actually really tricky to categorize because they are usually very small. Sometimes the pictures are blurry. And also they have ranges. So for example, if I just give you a picture of a butterfly, it's hard to say what it is. without knowing where the picture was taken, even like what season it was, even sometimes the time of day matters. And scientists have been trying to measure the impact of climate change on insect populations and butterfly populations for the last couple of years, but it's hard because, you know, you can go out into, so what typically they do is once a year, they'll go out into like a forest or like a park, and they'll count the butterfly species they see, but they'll only do that a couple of times a year maximum, and there's only so many entomologists. So they actually, some researchers from several institutions created a citizen science website called eButterfly, where people actually were submitting these pictures of butterflies, and they had hundreds of thousands of images and labels. And so we partnered up with them to develop an algorithm that actually identifies these butterflies using both the image data and the spatiotemporal data. So I'll spare you all the details, but you know, it was a bit complex because on one hand you have the actual picture someone took, but then you have like all these non-image information that you also want to use. So there was kind of like complex ways of putting them together and making sure that, you know, you represent time as a continuity and not just as a range, you know. So, but finally, our algorithm is deployed on their website and on their mobile app. So now people can take butterflies, pictures of butterflies in their backyard, and get suggestions of what these butterflies are. And so hopefully it's going to help people track biodiversity. And I think the last project I want to talk about is kind of a meta project I've been working on. So what I realized, there was this article that came out by Emma Strubel and her colleagues a couple of years ago about the carbon impact of machine learning, of AI. And so what we realized is that there's no tools for essentially measuring how much CO2 we're emitting, how much greenhouse gas we're emitting when we're running our models and our algorithms. We just assume that it's zero, but it actually exists because even if it's a cloud instance or even my home computer or some cluster, there is a carbon footprint. And so first we created MLCO2 impact, which was a calculator where you just enter the information about your algorithm, your model, how long it ran, what the hardware was, where the energy was coming from, and it spits out an estimate. And after that, that became an actual Python package called Code Carbon that will run in parallel to your code. And at the end, we'll spit out a CSV file with an estimate of your emissions and a comparison with like miles driven in a car and things like that. And the idea is to get a better handle of our environmental impact as a field as well, and not just say, oh, well, it's in the cloud, so we don't have any emissions. So that's something else I've been working on. If there's anything that you would retain from this presentation, there's so many different data sources that are useful for fighting climate change. Really, textual data, citizen science data, sensory data. I mean, we've seen so many examples already. And I think that's really empowering because you can really pick and choose what you're interested in, what you're good at, what people will use finally. And so there are lots of opportunities to get involved. Thank you for your attention. If you have any questions, you can reach out to me at my email or on Twitter.
Thank you, Sasha. It's you made me think that now I will need to track the carbon emission of any of these big algorithms that we run in our group. It's going to be,
you can use Code Carbon.
Fascinating and scary at the same time. So thank you. This was, and congratulations on the butterfly project. Sounds phenomenal.
Thanks.
Excellent. So we're going to turn to Jessica.
Great, thank you. So I'm going to give you guys just a brief overview of my research on data-informed models to advance climate solutions. And, let me just start with a brief motivation to look at what does successful climate change mitigation look like. And what I'm showing here are a number of trajectories that are estimated for keeping global temperature rise below 2 degrees Celsius. And essentially what's required is in order to, stay within this temperature target and limit the damage of climate change, we would need to see a very rapid reversal of rising greenhouse gas emissions trends, where the emissions would have to fall faster than they've risen for over a century. And to limit global mean temperature rise to less than 1.5 degrees Celsius, which are the scenarios shown here, the reversal would have to be even more dramatic. And 1.5 degrees Celsius is expected to be a safer target. So either way, time is short and financial resources are always limited, they're not unlimited. And my research is all about informing technological innovation, toward this future with the goal of developing and using data-informed models that could allow us to be a little bit more deliberate in our development of technological solutions, and hopefully ultimately to increase the success rate in these investments and the development of the technologies that are really going to be needed to essentially remove carbon from the energy system and also address other sources of greenhouse gas emissions. So the idea is really to use data-informed models to stretch each unit of time and investment further is one way to think about it, by increasing our success rate. And so I wanted to give you a very brief overview of my group's research. It's the Transic Lab at MIT, and I'll talk about the objective of the research, very briefly review the methods, give some examples of the results, and then talk about the impact, because the work doesn't stop with publishing papers, but the goal is really to inform decision-making. So the overall objective is to understand and inform technological innovation, especially in clean energy systems, to accelerate equitable climate solutions. And specifically, I focus on understanding the feedback loop shown here between emissions reductions and technology development. And my goal is to develop insight to inform interventions at various points in this process, involving government policy at the top, private investment, investing in capacity increases, and also engineering to improve these technologies. The methods that we develop are what I call data-informed models as a category to cover both mechanistic models that are testable against data and data-driven models, a different type of model that's not mechanistic, but data-driven, to measure technological innovation, try to understand the drivers. And sometimes that involves, understanding very fundamental questions about what drives technological improvement, and then identify performance targets for components of the system, components that various decision makers have agency over in developing. And this work is applied across scales, from materials to devices to infrastructures. And I take a very broad definition of technology to include hardware and a whole suite of non-hardware technologies that involve some form of codified knowledge, including, codified business practices, for example. The results fall into two main buckets. One is new knowledge of the drivers of technology innovation, sort of what's driving that feedback loop, and then also estimating quantitative targets that collective innovation processes can work toward. What are we aiming for as a result of that feedback loop? So I want to give you just two examples of projects. One was on understanding the reason why solar energy's costs had fallen by 99% over 4 decades. So solar energy is often held up as a success story for clean energy innovation. But the question we wanted to answer here, the very fundamental question, was, where did that success come from? And, when I would go around kind of polling various people in research and government and industry, there were a lot of ideas for where the success came from, but we really had to develop new theory to really pin down quantitatively what the drivers of that cost decline were, with the idea of then also developing a model and general insights that we can use to inform priorities for the future for solar energy, but a whole host of other technologies and even infrastructures. So what we did was we started with a very detailed engineering model where we have these 5 variables and p variables. Really, any technology can be represented as a set of usage ratios, these 5 variables, and p variables are input prices. And often many engineering efforts work at this level of really improving this set of variables in these 2 categories. From there, we developed a methodology to look at performance change, in this case, cost change, that relates to the engineering and really the physics of the underlying device. And then from there, we could look at higher level mechanisms, including those that involve human effort and emergent phenomena, like what I'm showing on the right, research and development, learning by doing, and economies of scale. And so we were able to draw conclusions about the drivers of innovation at each of these 2 levels, and also at the policy level. Importantly, at the policy level, we learned that we estimate that about 60% of that cost decline came from policies that stimulated market growth, and about 30% from policies that involved government investment in R&D. So the market growth, where that improvement came from, is from stimulating a lot of innovation in the private sector. So this relationship between policy and private sector investment is really important to try to recreate for other clean energy technologies going forward. I also want to give you just a quick example of some research that we did on targets. And here I'm talking about targets for charging infrastructure components, including where to site chargers, what their power should be, how predictive our models are for when people would stop and where for how long. And using this information to identify priority locations for rapid and equitable electric vehicle adoption. So in this work, as you can imagine, it really involves examining behaviors, how people are driving their cars, where they're stopping, for how long, and then also looking at technological limitations. What are the battery capacities? What battery capacities are affordable? Not everybody can afford a Tesla Model S, for example. What are the charger powers and costs, and sort of trying to, from all of this big mess, identify a small number of locations and strategies for charging powers that can be very effective across a range of different growth scenarios. And what we did was we ended up with identifying some key locations that can be mixed and matched depending on where you are in order to support electric vehicle adoption to inform policy efforts and also private sector investment. So as I mentioned, the work doesn't stop at the level of publishing papers. We are interested in developing new fundamental insight about technology innovation and behaviors and so forth, but really also orienting that insight to decision makers. And so the goal of the work is to inform, sometimes it's materials development, technology, and infrastructure decisions by engineers or private investors, policymakers, and sometimes the public. So I'm going to just quickly go through some examples of that here. So for example, some work that we did on stationary energy storage, looking at how we can estimate cost targets for stationary energy storage to support an increasing amount of variable renewable energy in the power sector, and sort of balance the variability in the solar and wind energy resource, and also considering energy demand fluctuations. We wanted to know, what cost targets should we collectively be going for stationary energy storage. And so we looked at that here and estimated, a cost target that is informing engineering development in this area. Some of the work that I've done is focused on forecasting technological change, obviously always under uncertainty, in order to inform investment portfolios and private investment, balancing the need to diversify, to manage uncertainty, and also concentrate in order to stretch each dollar further, concentrate in successful solutions, and finding the right level of concentration and diversification. Our work has also provided, as you'll hopefully have gotten a sense of before, it's provided strong evidence for what's referred to here as a mutually reinforcing cycle of emissions reduction and technology innovation. And this was evidence that informed discussions leading up to the Paris Agreement, I think can provide a strong motivation for investing in emissions reductions, because you get this additional payback of innovation. Obviously, there are many other reasons to invest in emissions reductions, but this is something that sort of speaks to an additional benefit for economic growth and economic well-being, and job creation opportunities and so forth. And then finally, I just want to give you an example of some of how we've taken the results of this work and presented the results in public-facing apps, such as the carboncounter.com website that's shown here, that allows consumers to compare the costs and the emissions, so the costs on the x-axis, the emissions on the y-axis, of different vehicle models they may be considering for their personal vehicles. And really the sort of insight from looking at this plot when we did this was, okay, you don't have to pay more for a lower emitting vehicle, but there's also a lot of diversity in the functionality of technologies and so forth. And what this site does is really allow people to explore their options. And it's been really great also as a way to interact with people from around the world that write with feedback and talk about their own car purchasing decisions. So that is the end of this. I've come to the end. And, I just invite you to be in touch if you have further questions, and also if you're interested to visit our website. So thank you.
Wonderful. Thank you. Thank you so much, Jessica. So I think, first of all, I would really like to invite the attendees to write question. If you have any question for our panelists, to put it in the chat. I'm just going to start the conversation and the discussion with one question, and then I will turn to the attendees for the question they have for the panelists. So first of all, thank you so much for all of you to share with us your really exciting research agenda. And I think one thing that made me think about is that when you're thinking about the intersection of data science and climate change, what are the many, many different ways that we can have wonderful and important impact? And so just to summarize for a moment, I think that, Ronita made us think about the built environment, including sensors and the design typology. And then we have Sasha both thinking about the climate change of financial disclosure as an important to think about the carbon footprint of the market, as well as tracking tracking butterfly to assess biodiversity. And then with Jessica really thinking about the data to inform models and to inform climate solution, and really to stimulate innovation. So I'm just going to start with my first question to all of you. So first of all, I am absolutely struck by your brilliancy and your leadership in trying to understand and mitigate climate change. Now, the question is interesting because all of you properly so have mentioned impact and the importance to go beyond the research publication, which clearly we have to have. So the question I have for you is, in your experience, what has been the best way to have impact? So to connect with policymakers, company, and profit and public, what really seems to work and do well? And I'll start with, I'm gonna go just around with Ronita, Sasha, and Jessica.
Thank you so much, Domenici, because that's something has been my primary goal from the beginning, to have impact, because research can be limited to only a group of people who understands, but impact actually is quite widespread. Especially I realized while working with both different levels of stakeholders, typically policymakers, as well as people whom we can directly impact, their expectations can diverge drastically. And so if we can we have done that exercise when we mapped out expectations for a single policy, we realized that the expectations were so different at the bottom of for the stakeholders who are at the bottom of the pyramid, whereas for the stakeholders who are at the real decision-making platforms. That's one. And secondly, I have realized that impact can also be from the aspect that we make the policymakers realize that this is probably something which the policy is currently missing. And I have been told by policymakers that, well, we never thought this angle, and that kind of opened my eyes. Secondly, when we kind of trained the women to do their own films, film their own lives, they had the agency to show whatever they wanted. So we were not the people who were deciding what to record and what not to. That made, and then when we did a feedback workshop, they said, we never realized we did so much work. We never realized that we were living in such a we were living in such polluted spaces. So I think it's this feedback mechanism made them real, because we also showed them simulations that, see, when you're cooking, this is the amount of smoke you are actually inhaling, which you're not seeing at all, which is not visible. And that's why my primary concern was, because majority of these kind of women normalize ill health or loss of health after a certain age, and they don't feel that it is a point of intervention, that they have to go and seek medical help. And that was quite a big revelation for me, because we generally tend to seek help whenever we feel our bodies are not reacting normally. And we found women coughing, and they said that, isn't it normal after 40 that I should be coughing? I saw my grandmother do it. I saw my mother do it. And this aspect kind of, I said that until I show them that what exactly they are experiencing every day, I may not be able to push them to change their behavior of just opening their windows during cooking, but at least few will be converted. Third impact, which we saw, that when the research got publicized, and because these are very sensitive, vulnerable areas, the government realized that probably something needs to be done. So although what we recommended was something needed much more discussion, they at least went back, and the people called back and told me that the government the municipality have come and painted their houses, clean their corridors, and the sanitation facility has improved. So I think the impacts are at three different stages. One is sometimes policies are very myopic, and just primarily because policies are made by siloed ministries. And so this has been my experience till date, and I think this is something which I'm seeing across the world in different parts of the world where I'm working currently.
Thank you. Sasha.
Yeah, something that I've really found that was surprising is it's really important to scope projects in a way that is not only reflective of our own perception. So like the butterfly project was kind of an idea, an example of that, because we had all these ideas of, machine learning can do that, and we can help with this and do that. And then it's really hard actually to stop and listen. And then it takes a lot of time, which, you're like, oh, let's train a model, let's get the data, let's get it going. But actually, I think we spent at least 2-3 months just discussing how the data is gathered, how it's labeled, what's useful, what are the technological constraints, can we do this, can we do that? And in the meantime, I learned so much about entomology and the impact of climate change on insects, and it was like a whole new world. And so, but I feel that, it is hard to stop and take that time, because often you want to, hit the ground running. And it's like, it's not really a methodological thing. It's not really a technological thing. So people tend to overlook it and then kind of jump headfirst into projects. And so that's why I've always been, every time I try to start a new project, I say, okay, well, at least 2 to 3 months is going to be, no coding. Don't touch any code. No, we're not touching the data. We're just going to talk about it and learn each other's vocabulary. And then when that's done properly, or at least taking the time to do that, then you can really, for example, figure out how to measure impact, right? Because it's not just going to be your accuracy metric or whatever you want to train your model using. It's going to be so much more than that, because, your model gets 99% accuracy, but then you overlooked that and that and that. You overlook the fact that it's highly memory intensive. You overlook the fact that there are these minority species that it doesn't cover. So, these are all things that you don't even think about until you've talked to these people. So I think that impact is contingent upon kind of connections and common understanding.
Yeah, that's a very good point. Jessica.
Yeah, great. And just to echo your comments, Francesca, it's really fantastic to hear about the work that the other panelists are doing. So I'm excited about that. But yeah, on this question about impact, I guess I have 2 comments. One is that, when I started doing work in this area, I was really trying to bridge 2 fields, economics and engineering, in the sense that in engineering and the development of technology, I think we often design technologies to be, optimal just in the next time step. So we're not necessarily designing technologies for a collective innovation process. And then in economics, we're often representing technologies after the fact, not including their physical characteristics or their drivers. But I think to really be more deliberate about technology innovation, we need to kind of bring some of that insight from economics on longer term trends into the engineering, and then bring some of the engineering into the economics of technology innovation. So that was one of the main drivers for me in developing this research area. And I think to kind of make a case for it, it was really important to talk about why it's important in real world examples, better investment in technologies to address climate change, or, more successful solar panels. So I think from very early on, I was thinking about those applications and thinking about even framing the very theoretical questions. And then the other comment I wanted to make is that one thing that's been surprising is that oftentimes when we're talking about applied impact, we think that a certain thing is going to be the most important. So when we were looking at an analysis of the Paris pledges, we thought that perhaps the estimates, the forecasts of how much costs would come down for different like clean energy technologies, solar and wind, we thought that the forecasts of those costs would be the most impactful thing, which is kind of more of an applied insight. But I think what actually ended up being most helpful was the fundamental insight, which is that these market creation policies, they can be in the form of emissions reductions. They can actually drive, and they have in the past driven very substantial technology improvement. And we could really pin that down with the theory that we developed and the mechanistic models that we were able to test against data. So that, and I've seen that in other examples too, with the electric work on electric vehicles. One of the most, I think, impactful findings was around the energy distribution that people have in their vehicle days, and the fact that even across very different types of cities, the way people drive, there's certain similarities such that the vast majority of days can be electrified, even with a low-cost electric vehicle, but that there's this heavy tail in that vehicle day energy distribution that poses a greater challenge. And we need to design charging infrastructure and other solutions around those high energy days. So anyway, I guess the basic point, that second point, was that it's a little bit counterintuitive, but for people out there and students and so forth, sometimes the reason why some of these applied questions are hard is because we don't have the underlying theoretical insight that we need. And you may want to go directly to finding the right answer, in an applied sense, but you may actually have more impact if you're really getting into explaining and developing more explanatory results and sort of what's driving the system.
Yeah, that's good. That's wonderful. So we have some really interesting questions from the audience. I'm going to start with a question that will be really directed to all of three, and I will appreciate some being very brief in your responses, so then we can cover as many questions as possible. So one question which I thought was very interesting is about education. So someone is asking, what would you say are the key things someone should look for it in a data science curriculum when looking to impact climate change, as in focusing on coding or statistics or climate science, or trying to get as much as all three as possible? What are your thoughts?
I think that it's hard to cover a lot of ground because there's a lot to learn about climate change and climate science, but reading some kind of high level things like the Tackling Climate Change paper, or there's others, I'm not just promoting that, but I mean, and getting a general idea, for example, like what are the main problems in transportation and electricity, et cetera, et cetera. And then once you've kind of picked a more concrete area, then digging down. And it's actually really important to understand, like, if you're looking at electricity systems, what's the difference between electricity and energy? What are the metrics used? All these things. But you can't do that for all areas. So I would kind of go breadth first and then depth first after you've picked an area.
Any other comment from the panelists?
Yeah. I mean, I could just say something. I think, it's really important to cover the technical and methodological subjects, such as, as was written here, coding, statistics, et cetera, mathematical analysis, but also to cover the domains. And then, but the thing is, I think actually what's the most critical is to give students experience and really teach them how to identify the impactful link between the two, so that they can actually formulate questions that require some, and they can develop bespoke methods or draw on existing methods to address those questions. But it doesn't really, like, the parallel track of learning about the domain and the methods, I don't think really works that well. It's really the intersection that can be hard, and sort of finding what is that sweet spot in where we're methodologically limited, and it's a really important question also. And so really addressing that, I think, is really important for these data science programs.
Yeah, if I may just add, because I've been using that to teach undergraduate students, I think what was very essential is they recognize that there are certain methods available in different disciplines, and using that in data science, trying to understand the philosophy behind it rather than the skill of doing coding, would be more essential in formulating these innovative questions and speaking to each other. Probably in that's I've always kind of advocated that interdisciplinarity is the forward of data science. So if we are not doing that, probably we are repeating we are just repeating an advancement of skill set, not really a innovation or thought process.
Yeah, great, thank you. So we have a question for Jessica, and they're asking, what kind of mathematical models are you using on the slide with the first example? For example, were there solution for a PDE or ADE, or were they just direct discrete time dynamics from the data without assuming an underlying system?
Yeah, so we had to model the underlying system, and we developed actually a bespoke method. And the way to think about it is it's a kind of discrete formulation of a PDE. That's kind of the best way to describe it. And so, yeah, I'm happy to provide more details, but the underlying methodology can be used to study any technology. It can be, a physical technology or an infrastructure. You need to understand the underlying physics, which is the underlying system. And then we're often dealing with, values for each of the key variables that measured over time in discrete intervals. And so that was really what required some methodological development.
Thank you. I have a question for Ronita. So for the building type screen, did you find out that there were some such differences between the architecture type and percentage of disease? Is it because there is not enough ventilation between the architectures? Did you find out any correlations between the increased percentage of disease and climate change regardless of the architecture type?
Yeah, so I would say a part of it is definitely with ventilation, but another part of it was with the culture of using windows and how they view windows and corridors. So it was the cultural meaning of those places. So when one community behaved in a different fashion, so they blocked, essentially it affects ventilation. So as well as daylight, because these are both required for making an inactive tuberculosis bacterium or even virus for that extent. And yes, when we were looking from the heat stress point of view, it did have, the typology had quite a strong relationship. The typology as a whole, not the design, had a quite strong relationship with the heat stress that it was responding to. And also the chain of events in terms of uptaking of appliances because of moving into a newer house. So there's definitely an intersection of behavioral studies and engineering modeling that can be built, and that's my endeavor. Yeah. So definitely we are looking at both of them.
Thank you. So a question for Sasha. So climate vulnerability disclosure. So this is really to identify companies who will suffer from the effect of climate change, nor not the culprits, correct? Is there something analogous that will help investors to clean their portfolios of contributors of negative externality more directly? This is a very provocative question.
It's an interesting question. So actually, technically, in theory, companies are supposed to disclose both their emissions and their vulnerabilities. In practice, not everyone does that. And we were focusing on the vulnerabilities because the sustainability analysts we were working with were focusing on that. But something that I've been trying to launch a project around is actually the emissions aspect of things. But it's a really silly thing. But most of these emissions are in tables in PDF files, and those are really, really, really hard to parse using NLP. So, you know, when you have a block of text and you have a sentence saying, we emitted 50 tons of CO2, you can get that number. But when it's in a table, then you have some column and row names, it's really difficult. So we got stuck with that, saying that like there are these pages and pages of tables, but we have trouble getting them. And it's actually a really interesting question that would be really useful because once again, like you have to scroll through 75 pages to get that specific number you want. And for example, depending on the scope of emissions you're focusing on, you need to really like go to the right cell. So I think there's definitely people working on this and empowering them with machine learning tools or data science tools could be really useful. And as far as I know, it hasn't been done yet.
Well, so we have a few minutes left, so I'm going to just ask a last question to all of you. So do you find that there is tension between technological improvement and regulatory policies, which achieves optimal social and climate outcomes? If so, how do you navigate this tension in making policy recommendations?
Say just a couple of things. You know, I think there's a couple of sort of risk factors, I guess I would identify. One is that we're not always on top of how technological improvements could be leading to negative externalities. So I think Sasha's work is a great example here. And also I think in Ronita's work, you know, thinking about areas that are less studied in terms of their impacts and sort of the technologies of informal settlements and so forth, looking at their impacts. So I think that often we're missing impacts of technology and then reacting after the fact. So it's good to sort of stay on top of that, and then policy can hopefully more successfully address those impacts. You know, one of the challenges with automation, if we're talking about automated vehicles, is that it could greatly increase demand if algorithmic development is not focused on that issue. So it doesn't have that in mind and isn't sort of coupled with policy to reduce greenhouse gas emissions. You could have a huge explosion in, you know, demand for travel and greater greenhouse gas emissions, you know, which would be really problematic from a climate perspective. So I think often we're not kind of studying all areas equally and all technologies equally. And then on the other hand, we're not always on top of the new technologies and the externalities associated with them. So that is something that's important to do better for better informing, not so much reactive policy, but like proactive policy.
Yeah, if I may just add, I have come across, because of my work majorly in the global south, sometimes we only see technology from an efficiency aspect and we miss out how technology is viewed. So it's very simple. So solar cells and PVs would have very good impact in rural areas where grid is difficult to be kind of installed immediately, and microgrids are very important. But when we asked these people why they are reluctant to do that in their houses when it's fine in their farmlands, they said, once we accept this, the government is never going to connect us to the grid. And so it's about security, how a technological innovation can be viewed from an aspect of efficiency versus how it is viewed actually where it will be implemented. So different communities will have different insecurities towards adoption of a technology. And I think somewhere we need to understand those hindrances. And it's not just behavioral change, it's about the meaning of that technology in a particular community.
Sasha,
last words. I think that
word.
that impact assessment is really important, that essentially we improve what we measure, and it's important to make sure that we're measuring the right things. So for example, focusing on different measures, not only more quantitative ones like the ones that we like output of electricity and things like that, but also qualitative ones like people's perception. And I think that obviously it's harder, but putting those two together and helping make decisions, not just saying this is more accurate or this has a better productivity, but also saying, and the qualitative aspect, we did a survey, we did blah, blah, blah. So putting those two together is more work, but ultimately, hopefully better in the long run.
Great. Thank you so much for your brilliancy and for doing such important work for the world. And with this, I'm closing the panel and I'm turning to Erin. Bye-bye.